Every computer you've ever used, your phone, your laptop, even the machine running this video, ultimately works with bits. A bit has two possible states, 0 or 1. But what if a computer could use the strange rules of quantum mechanics to do something completely different? Something that doesn't have to be simply 0 or 1. This is a qubit, the basic unit of information in a quantum computer. Let's start with an ordinary bit. Imagine a tiny switch. It can be off or on. We represent these possibilities as 0 and 1. A classical computer processes enormous numbers of these bits, manipulating zeros and ones to perform calculations. Everything from displaying a photograph, to running a video game, to simulating a weather forecast, can ultimately be reduced to information encoded in bits. But quantum mechanics gives us a very different possibility. A qubit, or quantum bit, can also have the states 0 and 1, but it can also exist in a superposition of both. Mathematically, we can write a qubit as sao a sao 0 plus v hu onsi 1. The symbols a and v are called probability amplitudes. Their squared magnitudes determine the probabilities of measuring 0 or 1. So before measurement, a qubit isn't simply an ordinary bit that secretly has one definite value. Its quantum state can contain information about both possibilities. One useful way to visualize a qubit is with something called the block sphere. The North Pole can represent 0, the South Pole can represent 1, and every other point on the sphere represents another possible pure quantum state. Unlike a classical bit, a qubit has an entire continuum of possible states. But there's an important catch. When we measure the qubit, we don't read out an infinite amount of information. The measurement produces a definite result, 0 or 1. This is where superposition becomes important. Imagine a quantum particle taking two possible paths. Classically, you might expect it to take one path or the other. Quantum mechanics allows the particle's state to involve both paths simultaneously, and those possibilities can interact with one another. This leads to one of the most important ideas in quantum computing, quantum interference. Quantum amplitudes behave like waves. When quantum states are combined, their amplitudes can reinforce one another or cancel one another out. This is called interference. Quantum algorithms are designed to exploit this behavior. The goal isn't simply to try every possible answer simultaneously and magically read them all. Instead, a quantum algorithm manipulates amplitudes so that incorrect possibilities can interfere destructively, while useful possibilities become more likely to appear when measured. That's where the potential power of quantum computing comes from. But qubits have another extraordinary property: entanglement. Two or more qubits can become linked in a quantum state where their properties are correlated in ways that cannot be explained by treating them as completely independent systems. Measure one, and the outcome can be strongly connected to the outcome of the other, even when the qubits are separated. Entanglement is one of the defining features of quantum mechanics, and a crucial resource for many quantum algorithms. So how do we actually compute with qubits? We use quantum gates. Classical computers use logic gates such as AND, OR, and NOT. Quantum computers use operations that transform quantum states. For example, the Hadamard gate can transform a qubit initially in state 0 into an equal superposition of 0 and 1. Other gates can change the phase of quantum amplitudes, rotate states, or create entanglement between qubits. A sequence of these operations forms a quantum circuit. But building a quantum computer is incredibly difficult. Qubits are extremely sensitive. Interactions with the surrounding environment can destroy the delicate quantum properties we need. This process is called decoherence. Heat, electromagnetic radiation, vibrations, and unwanted interactions with the environment can all introduce errors. That's why many quantum computers require extraordinarily controlled environments. Some superconducting quantum computers operate at temperatures extremely close to absolute zero. And quantum computers don't just have to protect individual qubits. They also need to deal with errors during computation. This is where quantum error correction becomes essential. Instead of simply copying a qubit like an ordinary classical bit, quantum information can be encoded across multiple physical qubits. Carefully designed measurements can detect certain errors without directly measuring and destroying the encoded quantum information. The dream is to build fault-tolerant quantum computers, machines capable of performing enormous numbers of reliable quantum operations despite imperfect hardware. So what could quantum computers actually do? They aren't simply faster versions of ordinary computers. For many everyday tasks, a classical computer will remain the better tool. But quantum computers may have major advantages for certain problems. They could help simulate molecules and materials, because nature itself operates according to quantum mechanics. They may improve certain approaches to optimization and search. And powerful quantum algorithms could potentially solve mathematical problems that are extremely difficult for classical computers. One famous example is Shor's algorithm, which, on a sufficiently powerful, fault-tolerant quantum computer, could efficiently factor large integers. That has major implications for modern cryptography. But here's the catch. Having more qubits doesn't automatically make a quantum computer more powerful. The qubits must remain coherent. The operations must be accurate, and the entire system must be carefully controlled. A machine with thousands of noisy qubits may be less useful than a much smaller machine with high-quality, well-controlled qubits. That's why scientists and engineers are racing to improve qubit quality, scalability, and error correction. So, what exactly is a qubit? It is the quantum analog of a classical bit. But unlike an ordinary bit, a qubit can exist in a superposition of quantum states. Qubits can interfere, they can become entangled, and they can be manipulated using quantum operations to perform computations in fundamentally different ways. The strange part is that we don't fully understand how useful large-scale quantum computers will ultimately become. Perhaps they will revolutionize chemistry, materials science, cryptography, and computation. Perhaps some of their promised applications will prove harder than expected. But the principle is already changing how we think about information. Because in the quantum world, information isn't merely something stored in zeros and ones. It can exist as a quantum state, with amplitudes, phases, interference, and entanglement. And that tiny quantum system, the qubit, may become one of the fundamental building blocks of the computers of the future.